Hi, welcome to this talk about reflection and Android. So we are going to present a few researches that we've been doing at Groupon. My name is Stéphane Nicolas. I'm a senior Android developer at Groupon now, working in the Android team. I got around 20 years of Java coding experience. And I also participate in a couple of open source softwares like ROBOGUICE, ROBOGUICE, Boundbox, Injects. Most of them are related to Android, but not all. Some are more pure Java stuff. So yeah, I work at Groupon, and yeah, we are hiring. So if you want to spend some time in California, actually it's a great team, a great environment to work there. So feel free to join us. So today, what are we going to talk about? We're going to talk about reflections, no reflection. It's a project we started like 2 years ago. Our main focus was trying to improve the performances of dependency injection in Android. I come back to that. So we have been working on trying to find alternatives to reflection on the Android platform. So we'll talk more in depth about our motivations, also explain what is reflection, and we could identify some alternative technologies that we could use instead of reflection, so we're going to talk about that too. And then I will introduce a new technology that we've been thinking about and developing during the last month, which is called reflection, no reflection. And then we will have a conclusion about all this research work. Prior to this talk, I would strongly recommend that you have some background knowledge of dependency injection, DI, and bindings. By this I mean like stuff like butter knife, Dart, so everything that can assign a value to a field basically inside an activity, a fragment, whatever. And some background knowledge also of annotation processing. So we will have some reminders during the talk. So what are our motivations at Groupon? Why do we study reflection? Basically, we have developed during the past years dependency injection called ROBOGUICE. ROBOGUICE is actually based on juice, as the name says it. So it means that it's a very old technology from Java. It's feature-rich. It has been developed for almost like 6 or 7 years now. It's very stable. It offers a couple of very advanced features for dependency injection. It's very easy to configure. And if we would want to compare it to Dagger 1 or Dagger 2, for instance, the other popular dependency injection frameworks on the Android platform, there is actually no requirement to manually define the graph of injections, which is quite a big advantage when you think about it. There is a lot of boilerplate code that has been introduced by Dagger 1 and even more by Dagger 2 to define this graph, but with Juice you don't need to explicitly do so. But Juice has a problem, it's that it's slow. And so ROBOGUICE is also told to be slow. So we will detail that a bit more in a couple of seconds. So in ROBOGUICE 3, our latest release last year, we actually improved the performances of ROBOGUICE by 35%, which is quite a lot. So the way we did it is that Juice was based uniquely on reflection, and we introduced an annotation processing phase at the very beginning of the compilation, so that we can skip some part of reflection or boost them, make them faster. If you want to know more about what we did, we have some slides on speaker deck. We introduced a technology called Blender and RoboBlender, an annotation for Juice, an annotation processor for Juice. So let's compare exactly the performances of the different dependency injection on the Android platform. So I'm going to show you a couple of numbers that have been produced on Genymotion, which is a very fast Android emulator, as most of you might know it. So let's say you got a class A, very simple, no fields, nothing, and you want A to be a dependency of some other class, and you want to inject A into this class. So you will have to build an instance of A and assign it as a dependency of our outer class. If you want to create 1,000 instances of A using the constructor call, then you can see that it takes roughly less than 1 millisecond for 1,000 creations of instances of A. If you do so using Dagger 1, then it comes up to 10 milliseconds. With the ROBOGUICE 2, we were actually much slower. It took around 30 milliseconds, roughly. ROBOGUICE 3 decreased that to like 17 milliseconds, and ROBOGUICE is making it a bit better. ROBOGUICE 4 is making it a bit better. But still, even if we could make large improvements, 35% is not enough compared to Dagger 1, so we wanted to improve that. And we think that the main cause of slowness of juice, of ROBOGUICE, actually comes from reflection. So if reflection is slow, let's try to kill it completely, to remove it completely from juice and try to build something that is juice-like and got the best of juice, that how easy it can be to use it, but more efficient and faster. So that's what we have tried to do, and I will summarize our research on that. So first, let's talk about reflection. What is reflection? So here you got a very simple schema that explains the cycle of development. So you got your Java source code inside your IDE, you send it to the compiler, Java-C, and then you will get some bytecode. The bytecode will be interpreted by the JVM, so it can be Dart, Art, or Dalvik, or a standard JVM. And then you got a running application. So reflection takes place when the application is running. Reflection gives you a way to actually see your own program when it is running. So you can manipulate classes, methods, constructors, fields. It's actually very simple and intuitive. It offers a very simple API, very close to the way object-oriented programmers talk about a program. So it's not very difficult to learn. As you can see, you can just define a class, find its constructors, scan through them, invoke them, same for methods, fields. So you can call methods, you can call constructors, you can assign fields. So reflection gives us the ability to modify actually the program when it's running. And we need to be able to do this to inject the dependencies. So that's our goal when using reflection inside Juice, is to identify all the dependencies that are annotated with @inject, all the fields, for instance, or all the methods, and to be able to call them, call the methods, or to assign values to the fields, to assign the values of the dependencies to the fields. But yeah, reflection is slow, especially on Android. So you might know that in Java, reflection is not so slow in pure Java on a JVM, because there is some caching policy. So by default, the 15 first calls to anything based on reflection on a JVM will be actually a bit slow. But after 15 calls, the JVM is going to cache the calls. And so all the code is going to be executed by a just-in-time compiler as usual. And so after 15 calls, everything goes very fast. But on Android, we don't have this technology. There is no JIT for reflection. And that's why it keeps being slow. But what exactly is slow in reflection? Because everyone says, OK, Juice is too slow. It's based on reflection. But what exactly makes it slow in reflection? So we wanted to get some numbers. Yeah. So what we did is to benchmark a few aspects of reflection. So as you can see on the upper right figure, when you scan fields to detect annotations, to see which ones are annotated, to scan methods to see which ones are annotated, this actually takes a lot of time. Loading classes via reflection also takes a lot of time. When it comes to field modifications, so you got a field, you want to assign it. If you do it directly, let's say it's a public field, you just assign it a value. For 1 million field modifications, it would take roughly 1 millisecond. If you do it via reflection, then it can take 3 times more time. For method calls in the lower right corner, you can see that it takes a bit more time via reflection, but not so much. And actually, there is a huge difference when it comes to constructors. So if you instantiate 1 million objects by a call to the constructor directly, it takes like 200 milliseconds, still a bit slow. It's actually slow to create Java objects. But if you do it via reflection, it takes 5 times more time. So what are the alternatives? If we want to bypass reflection, what can we actually do? Let's come back to the central schema of this presentation and identify 3 alternatives. So what we could do is use bytecode weaving. So we can take the bytecode, make changes there, inject the dependencies, for instance, inside the bytecode directly. So that would be possible. A second alternative would be to use AST. So ASTs are abstract syntax trees. We will come in more depth to what ASTs are. And so it would also be possible to modify a Java program at this level. So between, let's say, the compiler and the bytecode. And there is a third alternative that is more popular these days on Android, which is to use annotation processing. So let's study those 3 alternatives. The first one is bytecode weaving. What is bytecode weaving? So bytecode weaving is an old term on the Java platform. I think the first time it's been introduced is like the second year after Java has been published. And actually, in Java, there are two ways to modify the bytecode. There is a dynamic way to modify the bytecode, and there is a static way to modify it. So on a standard JVM, you can use what is called a Java agent. And a Java agent will be more or less monitoring the JVM, and as soon as it loads a new class, the Java agent will be triggered, and the agent can do some bytecode manipulations at runtime. So this is possible on a standard JVM, but not on Dalvik and not on Art. There is no equivalent of a Java agent. Maybe we could use instrumentation, but it's much more limited. If you want a more in-depth talk about bytecode weaving in Android, I suggest that you go to Speaker Deck, and we got some slides also on bytecode weaving. But we wanted to study how really it would be possible to use bytecode weaving on Android, so we have created a full stack to do what we call static bytecode manipulation. So opposed to dynamic bytecode manipulation, the static bytecode manipulation would take place just right after the classes have been compiled. So you get like a Java class, a class file, sorry, and you are going to dig into that class file and manipulate the bytecode just right after the classes have been compiled, and they will be embedded into your Dex file, into your APK. So it is actually possible. It required quite a lot of work. We spent like 2 months trying to develop a full stack so that we could completely modify the bytecode in the way we want, something that is flexible enough. So we could achieve some good results. For instance, let's take this is an example of a library we've developed using bytecode weaving on Android. Let's say you got an activity, like this main activity that extends activity. You just annotate it with a simple annotation, like at log lifecycle. You add a Gradle plugin. And what we're going to do is to scan your bytecode, the bytecode of the main activity class, to identify all the methods that are lifecycle methods of your activity. And before they are called, we will log something. And then after they are called, at the end of the call, we will log something as well. So you can, for instance, measure the time spent in every method, which is part of the lifecycle of an activity. And as you can see, it's as simple as just annotating the class, and that's it, nothing else to do, which is actually quite powerful. So if we want to summarize what is good and what is wrong inside the bytecode weaving technique, you can see that it's very simple to use. It's actually, there is no boilerplate at all. What you do is just annotating, and then we will give meaning to these annotations via a library. The library is very easy to use. You just add a Gradle plugin to your build. It will interpret the annotation, modify the bytecode for you, nothing else to do. So we think it's actually very powerful, because you could change the behavior of a class in every way you want. And there is kind of a standard on the Java platform, which has been developed over time, which is called Java Assist. Most of the bytecode manipulations on the Java platform are done through this library, so it becomes like a de facto standard. On the bad side, let's say that the libraries that are based on bytecode weaving are actually quite complex, because you need to dig into the bytecode, you need to have to use some kind of reflection-like API provided by Java Assist. And they are also very difficult to debug, because you can do whatever you want with bytecode manipulation. You can do even very strange things, like a method with 2 return statements in a row. So you are at a very low level, and it's a bit difficult to understand exactly what troubles you can get into. So it's powerful, but it also comes with maybe too much power sometimes. One big disadvantage of this approach of bytecode weaving is that it has never been standardized. So inside the huge Gradle build cycle in Android, you might know that there are more like 100 Gradle tasks involved now. But there is no real room for, no official room for triggering something based on bytecode weaving. And one limitation of bytecode weaving, the way we can do it on Android statically, is that you can modify class files very easily. Jars also. Java Assist has been developed for Java, so it works with all that. But actually not Dex files. So for instance, if you got an AAR dependency, it would be impossible using Java Assist right now to actually open the AAR, open the Dex inside, and do some bytecode modification inside it, rezip everything, and use the AAR dependency. There is currently a fork of Java Assist to work with DEX files, but it has not been reached a maturity level still. Also, there is something coming up with the Android platform, the use of Jack and Jill, a whole new compiler. So the idea of the Jack and Jill toolchain, let's say, is to get a very precise idea of every change you make during the compilation cycle. So you change one line, we can identify exactly what place in the bytecode has changed, or what resource has changed, so we can know in the DEX exactly what has changed, and inside the APK exactly the small portion that has changed, and hopefully in the end we can even just send a small delta to the device, so when you are developing, we are not going to shoot a full new APK as soon as you do a small change, but maybe just a small delta of the APK, and we can use the new application. But Jack Engine is not official yet. We think it's going to be fully released during this year or 2016, let's say. And actually, Jack and Jill is not very well documented yet. We know that it's going to use a new format that is not the class file format, which is called JACE. And no one knows exactly the specifications of JACE. And there is no real announcement of any specification coming. So it looks like something very internal to Google. And we don't know exactly in which extent we're going to be able to modify the bytecode in this format. But we can come back to that because things are changing a bit on this side. And also one big disadvantage of bytecode manipulations is that the modifications that you could introduce with the library based on bytecode weaving are actually invisible to developers. So you are editing your source code, you just add an annotation, and we are going to manipulate the bytecode which is completely visible to you. So maybe we're going to introduce some stuff which you are not so confident about. And many developers fear that actually we're going to introduce behaviors or bugs that would be very hard to debug because they don't even have a source code associated to it that you could review. So that's one of the, those are the main disadvantages of bytecode weaving. But actually it works, and it works great even. We could also publish 2 or 3 other libraries based on bytecode weaving. One of them is directly the equivalent of ButterKnife. So we don't use annotation processing, we just use bytecode weaving. We did also the same for resources, not only views. Now ButterKnife does it also. And we also did the same for the extras, so that you can pass in an intent from one activity to another, and we could do some bytecode modification to actually inject the values of the extras passed to your bundle. So yeah, it works, but it also comes with a dark side. So let's study a bit more the second alternative, which is AST manipulation. So AST is an acronym that stands for abstract syntax trees. So abstract syntax trees are basically data structures that are used internally by the compiler, all of them. When I mean all of them, I mean Java-C, the official Java compiler, but also the alternative compiler of Eclipse. I don't think anyone uses Eclipse anymore. But still, those two compilers internally use abstract syntax trees. What they do is that they take the source code, they will transform it into an AST in a first pass of the compiler, and then after that, the compiler is going to compile the ASTs into a Java class file, into bytecode. But between the two, between the first pass and the second pass, we can actually manipulate the ASTs directly. A few libraries do that in Java. The very well-known Lombok project does this in Java. I don't know if most of you are aware of it. I think on Android it's quite fresh, not so many people use it still. So with Lombok, you can, for instance, just annotate a field, and Lombok is going to generate the setters and getters for you, for instance, one of the cool things it can do. Here you got an example of a library that's been developed really for Android by someone called Matus from Poland, if my memory is good. So he's developed a new project called Chryse, which I probably pronounce very bad. So for instance, with this project, you can transform a class into a parcelable very easily. So you can just annotate a class, extend the interface, and by AST manipulation, we are going to add all the methods needed to actually implement the parcelable interface. So the creator, the describe content method, and the serialization method. So just by using a simple annotation. So you can see it's very close to what we can achieve with bytecode weaving. This actually works, and it works pretty well. So you can create parser labels like that. And you can find the whole source code on GitHub. So that's also an alternative. So let's compare what's good and what's bad into AST manipulation, into this approach. So again, it's very simple to use. There is absolutely no boilerplate. You just have annotations to add. That's it. They are very easy to use. You just add a plugin to your build or to your IDE, but now they are pretty much in sync with if you use Android Studio and Gradle. And it's very powerful. We can do a lot of transformation, as much as we can do with bytecode weaving. On the dark side, we must say that manipulating the ASTs is even harder than manipulating the bytecode. Why? Because there is no standard library to do it, so you rely on something very low level. So there are some Java classes that represent ASTs, but you will have to do everything and you will be on your own, basically. So yeah, it's harder to make those libraries work. And even if you look at Lombok, it's a very complex project because it has been even designed to be able to run on both compilers, the Eclipse compiler and Java-C compilers. For HERC, for Android, the author just focused on Android compiler, the official Java-C compiler. But still, there is only one implementation to provide, but it's tough to provide it. Also, in the same way as bytecode weaving is non-standard in an Android build, it's the same here for AST manipulations. It's non-standard. And if Jack and Jill come into the play, then again we will have some trouble because we will have to manipulate the ASTs, but maybe Jack and Jill is going to use a completely different format from which it would be difficult to create ASTs, if possible. And again, those modifications are also invisible because they occur after the editing of the source code inside the IDE. Same disadvantage as bytecode weaving. Now let's focus on the third approach, the third alternative, which is annotation processing. So here is an example of annotation processing inside ButterKnife. So you just annotate a couple of fields, like the edit text username. You are going to bind it to an Android ID inside the layout. And we are going to, with ButterKnife, we're going to generate some new code. And there will be some boilerplate code needed to actually invoke the code that is generated during annotation processing. There is still some boilerplate code that is needed. Oh, by the way, it's something that is often funny to me, is that during this call, there is some reflection. So you cannot say when you use ButterKnife, you don't use reflection at all. There is some reflection to actually call the right code. You see that you just bind this, but internally, ButterKnife will load the generated code for you via reflection. So annotation processing is quite simple to use, not very complex. It's a Java standard, which is quite a big thing compared to bytecode manipulation and AST manipulation. It's really part of the official documentation of the Java platform, the requirement of a platform to be Java compliant. And it's relatively powerful, so not as powerful as would be the bytecode weaving or the AST manipulations. We will see why in a second. On the dark side, the API is difficult. I don't know if most of you have actually tried to implement an annotation processor, but it's actually tough. It's very different from reflection. It uses a whole new API, a whole new bunch of concepts, like type elements, which are a bit messy sometimes, not so easy to catch, really. Even if you are used to develop annotation processing, you will log a lot of stuff because it's hard to remember. It's hard to map mentally to what we use as concepts when we talk about a Java program. Also, one big limitation of annotation processing is that you can only create new code. So by design, the annotation processor has been limited so that there is no way that you can modify existing source code with annotation processing. There is no workaround. Well, actually, there is one little thing you can do. Maybe we can come up during the question period. So you cannot modify the program, but you can generate new code. And that's why you will actually require some boilerplate code to indeed call the code that has been generated during annotation processing. That's why you do the ButterKnife.inject this or bind this. The problem with annotation processing is actually what is happening, or what has been happening during the last 2 years on the Android platform, is that when Google decided to use Java, it was for two reasons. First one, to recruit Java developers, and we are billions of people knowing Java. It's not a very difficult language. We learn it at school. And those people could be converted into Android programmers. So that was a good guess. But there is also a second thing that is very compelling inside Java, is that we could reuse a lot of technologies, a lot of libraries. A lot of libraries that have been maturing during like 10 years inside the Java world, or 20 years. And we could reuse them on the Android platform. That was a real boost at the beginning of Android. So it was not something fresh, and everything would have to be rewritten. But if you want to bypass reflection, all the libraries that are based on reflection, and you want to make them very efficient on Android, you have to use annotation processing for now. It means that you are going to rewrite everything. And that's basically what has been happening. So Juice was not good enough. We had to rewrite it into Dagger 1, even Dagger 2. Butter Knife would have been possible with reflection, would have been a very simple library to code, but it had to be completely written from scratch so that it would not use reflection. And the same occurs for every kind of technology you can think of. For instance, ORMs are very popular in the Java world, but in Android, one bottleneck would be to use them because they are based on reflection. So we could create annotation processing-based ORMs, but it means we are going to rewrite everything, which is quite a big disadvantage. Also, you need some boilerplate code to invoke generated code, which is not as easy as just not having to write it. So let's try to dig a bit on what is happening during annotation processing. So you take your Java source code, you pass it to the compiler, and actually the compiler is going to fork. It will trigger a tool called the annotation processor inside the APT, annotation processor inside the Java-C compiler, and we will process all the annotations prior to compiling, and then it will generate new Java source code potentially, or you can even generate some other stuff. You can even generate class files if you want, but most of the annotation processors we know of actually generate Java source code. And then we will take the generated source code, the original source code, pass it to the compiler, and get bytecode files. Here is an example of some code that has been generated by Butter Knife. So we are binding a few text views, and as soon as Butter Knife annotation processor is going to run, it will create a $$ binder, which will assign all the views to their actual views inside the layout, the XML layout. So as you can see, the code that is generated is quite simple to follow. And this code will have to be invoked by a call using reflection, like butterknife.inject this. So what do we use actually annotation processing for? We use it for accessing fields, like here. We're just using those fields to assign them a value. We could also do that for calling methods, like in the case of Dagger 1 or Dagger 2, like the provider methods, for instance, that are invoked by some code that's generated during annotation processing. We can do the same for constructors for dependency injection, creating the dependencies. So we are doing exactly what we want to do with reflection. So both of them are kind of equivalent. We can do exactly the same thing as we can do with reflection. We can do them with annotation processing. But still, there are a couple of limitations. So no class modification, only new code, which means some boilerplate. Also, we lost something. If you look at the fields, the text views inside the activity on the top, on the right, you can see that they are not private anymore. They should be private. They should be private to your activity. But if you make them private, then the generated code cannot access them, because we are creating a new class in the same package. So the usual workaround is just to remove the private modifier so that they become package protected, and the generated source code can actually access them. Okay, it's not such a big deal, but still, we lost some power inside Java using that. With reflection, there is no such limitation. You can actually change the modifier visibility of a field or a method using reflection prior to using it. So when we see those alternatives, we were thinking, okay, maybe we can get the best of both worlds, no? Trying to make it easy to adapt reflection, all the libraries that are based on reflection, we could try to just adapt them a little bit, not to rewrite them fully, but just to modify them slightly so they would not be using true reflection. It would be nice to have that. Second, we want to take the best of reflection, which is ease, because we actually use a very simple API, a very intuitive API, and get also the best of annotation processing with the speed. So if we could combine those two into a single technology, maybe that would be great. And third, we're thinking that no one wants to see the generated code. When you're using butter knife, you usually don't care. And so it would be interesting to keep that properties and hide the generated code as well. So what we've been doing or thinking of is that we could generate reflection-like code via annotation processing. That is really the central idea inside reflection or reflection. So we want to use annotation processing to generate something that will be 100% compatible with reflection, but would actually not be based on reflection. Let's see how we can do that. So it will involve 3 steps. The first one is going to be to define what we call R&R, so for reflection or reflection, classes. So those classes are going to be 100% compatible with reflection, and we are going to fill those data structures during annotation processing time. So inside the annotation processor that you're going to write, instead of manipulating this awkward API that is used for annotation processing, it would be great if actually we could use reflection, because it's simpler. So what we're going to do is to generate classes that are fully compatible with reflection, but we are going to fill all the information those classes require, like how many fields do they get, how do they have, how many methods do they have, what are the annotations of the methods, the parameters, everything that the reflection provide. We are going to try to completely get all this information during annotation processing and create the data structures for reflection. So this only takes place during annotation processing time. The second step is once you got those R&R classes, then you could generate them. So if you generate those classes, then it will be possible to use the R&R classes at runtime, not only at annotation processing time, but during runtime as well. So you generate the code of the classes that you've been able to build during annotation processing, and you expose them to the runtime so they become available for the application itself in the same way as reflection is available. So we could do that. If we do so, we will have most of the features of reflection, except one, modifying a field or calling a method. So all the code that we can actually generate will hold all the information of reflection, but will not allow a write access like reflection does. So we decided to add a third step to actually generate new code that will allow to modify the application in the same way as reflection allows to do it. So we can invoke methods, invoke constructors, and assign value to fields. So I will detail a bit more the 3 steps. The first step is, so it takes place during annotation processing. The main idea is that you're going to take your source code, pass it to the annotation processor, then we're going to build R&R classes. So those classes, again, are exactly the same classes, or they expose the same API as the reflection classes. So we are going to create those classes, and from now, what it means is that you can create an annotation processor that is based on reflection. So instead of using the meta API of the annotation processing API, what you're going to be able to do is to use reflection to create an annotation processor. So it makes it much more easy to actually create annotation processors. And then the generated Java source is going to be sent to the compiler as usual. So at the end of the first step, when we could achieve that, the result was that we could manipulate fields, we could manipulate methods, we could manipulate constructors, we could scan all the classes, for instance, to ask for the annotated fields, annotated methods, just using reflections. So it means that you're going to use classes or methods, fields, before they are even compiled. That is really the node, what is central inside the annotation processing API. Why doesn't it use reflection by nature is that reflection is about classes, but annotation processing takes place before compilation, so there are no classes. That's why in Java they introduced a new API. What we did is to unify those two APIs so that you can manipulate the classes even before they are compiled, just by the view you get of them via the annotation processor. So using unification of annotation processing and reflection API, according to us, just by itself, this achievement is quite a good milestone in Java. We think it's interesting for the language itself, or maybe it can even demonstrate that maybe a language change is required, because we could do something that is much simpler at the annotation processing level, or maybe Java could change. So that was a good result. So the second step, remember, is to take those R&R classes that we have constructed during annotation processing and to generate them so that they are going to be available at runtime. We did that also. So we take the generated code to fill the R&R classes. We take the R&R classes that we generated and we generate the code for them. So we are going to create code that are going to be able at runtime to fill those classes again. I don't know if you can follow me, I hope so. So the first step was to fill reflection-like classes with data obtained via annotation processing. Second step is to generate code to recreate those classes and so that they are available at runtime. We are going to create code to create again those R&R classes at runtime. And so the application will be able to use the R&R reflection API. So we could do that, but the limitation is that it's going to be read-only, so no write access, no field modification, no method invocation, no constructors invocation. That's the end of the second step. Here is an example of what an R&R class looks like. So we generate code to create those classes. So as you can see, we generate code to create a class, which is not a Java class. Actually, you cannot create a new class like that. You cannot call new class in Java on the reflection classes. But with R&R classes, we do it this way. So we can define a class, we can define all the fields inside this class, we can define all the annotations of those fields, same for methods, same for constructors. So all this code can be executed at runtime and create a pseudo class-like, which has exactly the same API as reflection, but it will be available at runtime and will actually involve no reflection at all. It will have just been filled by code that is generated during annotation processing. So yeah, it's possible, and all that could work. So all our classes are going to be 100% compatible with the reflection API. We got even a bunch of tests to test that we're actually exactly compliant with the reflection APIs. We're going to use the classes that are filled during annotation processing. They are going to be available at runtime in pretty much the same way as you would use reflection. So for instance, you could use class.forName, a class name, and you would get an R&R class that you can use to ask for fields, methods, constructors. So after step 2, what we have as a result is that we have R&R reflection classes that are available to libraries and applications. They will expose something that is completely compliant with reflection. It will be available at runtime, and it's much faster than reflection. So you can ask a class, give me all your annotated fields, and for this class, it's just going through a hash map, basically, that's it. And there is no native code to actually open the bytecode, to look through the indexes, nothing like that. So it's much faster to use R&R classes compared to reflection. That's what we need on Android. So that's a result of step 2. One of the limitations of step 2 was that nothing was you couldn't modify anything, so it was only a read access to reflection information. So we decided to add a step 3. During this step 3, we are going to generate not only R&R classes, but also to generate what we call reflectors, class reflectors. Those class reflectors will allow a write access to the classes of your program. How we can do that? So here is what a reflector would look like. So here you got a reflector for a class A. So we are going inside the reflector to provide methods to actually assign values to fields, to actually call constructors, to actually call methods. So we're going to pass this reflector to an R&R class. Every R&R class will know of its associated reflector. and we will be able to not only read the information of reflection, but also to make modifications to the program itself when it's running, just by generating all the code that changes the program itself. And as you can see, the code that's generated doesn't use reflection at all either. For instance, if we want to use the first constructor of a class, then we're going to just call new A, and that's it. It's just some wrapper to call the constructor. But it gives you the feeling to use the reflection API. It's something very generic, but actually there is no reflection involved. That's the base idea. So we can use those reflectors to modify the fields, to access them, read or set them, to invoke methods, and to invoke constructors. As a result of step 3, we can now make those classes, the R&R classes, still available to applications and libraries at runtime. They will provide read and write access to reflection information, and still they are faster than Android. So we are going to generate a reflection-like layer of your own classes that is exactly the same as reflection, but it's going to be faster and not involve reflection at all. That's why we called it reflection, no reflection. So it means that if you have a library that uses reflection, let's say an ORM or a dependency injection library, you could just, instead of using the classes of the reflection API, you use the R&R classes, and that should be the only change you would have to do, and you would get the Android version, optimized, speed, efficient, to use for the Android platform, but not a big rewrite as we're doing right now. There are a couple of more details we can go through if you want during the question period. So actually one of them was to create annotation implementations. We could succeed in that also, but we decided not to have a slide dedicated to it. But it was very interesting from a syntactic level point of view. So, okay, up to now I explained you how we could create the R&R framework. So we got it working. Great, what do we do next? But basically, we wanted to do all that for improving dependency injection. So let's try to fork Juice. Let's try to see if that works. If we can reuse Juice the way it is using reflection, just change a little couple of packages, replace that by R&R classes, and we should be running. So we tried to do that. So instead of using Juice, which uses reflection for processing, accessing fields, invoking methods, invoking constructors, we tried to fork it to make it R&R Juice. And instead of reflection, we would use R&R reflection for everything from processing, accessing field, invocation of methods, etc. This actually was a great attempt. It took like 1 week, and it failed. It just failed. Why did it fail? Because Juice was using actually pretty much all the features of reflection, and some of them were quite difficult to implement using R&R. We could do it for most of them, but we were realizing that we were introducing a lot more changes inside the Juice source code. For instance, there are some things that you can do with reflections that are very tied to the very nature of a Java compiler. For instance, let's say you got a class. You call a.class, which is a class literal, and it's actually the exact same object as you would get with a.getClass, which is reflection. So on the left side, you got reflection, and on the right side, you got a compiler statement, which is a class symbolization. And there is no way we can achieve these kind of features with something that is not linked to the Java compiler itself. So R&R classes could not do that. You could not have these equals there. And actually, inside Juice, it was used quite a lot of time. So we could work around it, but it would mean to process the a.class to find the equivalent R&R classes, which would slow down the whole process for just an equal sign. And it was not the only trouble we had, but one of the biggest ones. And we just realized that, okay, R&R classes work and everything, but it's not as easy to change a library that is based on reflection to use something alternative. So okay, it failed, but we tried again. So we decided to take a different approach this time. Instead of using reflection, R&R reflection for processing, which means, for instance, comparing classes, as we just saw, what we did is just using the R&R classes for the manipulation of the program itself. So when you invoke a method via reflection, we would change that to R&R reflection, invoking the methods via RNR classes, sorry. And do it again for the fields, methods, and constructors. But just change that very ultimate process. Not use RNR reflection for the whole thing inside Juice, but just for the very last mile. We could do that, and that only. And actually it worked. It worked pretty well. We got some better results, like almost 30% performance gain. But then we are thinking that, okay, we gained 30%, so it makes it very close to Dagger 1 performances, very, very close. But still, we have introduced quite a lot of complexity to achieve that, and that was a bit disappointing. So as a conclusion, we think that, okay, maybe the biggest achievement of this research has been to show that we can indeed unify completely annotation processing and reflection. So maybe everyone could create its own annotation processor using this stuff, because it's as simple as using reflection and everyone is able to do it. So that's something that works and works well and is pretty stable, not very complicated. It doesn't add anything, any overhead at runtime, nothing, just makes annotation processing easier. Regarding step 2 and step 3, which is kind of a generalization of all the work that has been done in Android using annotation processors, we think that, okay, we can circumvent reflection. It's possible, but it's going to add a lot of classes, to add a lot of generated code, to add some quite tough steps inside the Java processing, the Java compiling step inside your build. It's going to add a lot of methods to your dexes also, to make the applications bigger, just to provide a layer of abstraction of reflection. And ultimately, all this complexity will come to like a 30% gain. Not so much. So we demonstrated that this approach is feasible, but we're not so happy about it. So we are thinking of, maybe releasing a new version of Juice based on that, but maybe not. We're not sure yet. We're still testing the technology and actually not so happy about it because it adds a lot of complexity. It also means to add a lot of maintenance to get in a direction that is, yes, it's interesting, but maybe a bit too big also for a company like us. That would be maybe more the role of Oracle or Google to do this kind of stuff. Maybe not our. So we are still considering a bit what to do with all this stuff. And also, we are thinking that after all, what we've been doing is trying just to improve the Android platform, but at the very programmer level, what we could do without the tools that were available to us and the knowledge we had. But the real solution could be elsewhere. When you think about it, if inside Dalvik or inside Art, Google would make some efforts to make reflection faster, that would pay off and would be much simpler. So that's something that maybe will change. Some people are considering to add a just-in-time for compiler for reflection, so everything would be ahead of time with Art, but reflection code would be compiled just in time. That could be possible. A second alternative, which looks maybe closer in time, is to use the new transformations APIs. So I don't know if all of you are aware, but inside the new Android Gradle plugin, actually it's still in beta. I think the version, not so sure, it changes so often. I think it's 1.5, not so sure about that. But they are introducing a new transformation API. So inside the Gradle build cycle, it will very soon be possible to do some bytecode modification. This transformation API has actually been needed by Google so that they could create the Jack and Jill toolchain to make it work, and still keep a couple of features that are related to bytecode modification. Like, for instance, code coverage. When you are running your test now, and you can do it pretty easily within the Android Studio IDE, so you can create a test and launch the application, and launch the test and see what lines have been tested and which lines have not been tested. To do that, you have to change the application under test. So in every line, basically, you would add some code to say if this line has been called or not during tests. So they are changing the bytecode. That's the way we do code coverage in Android. So they needed the transformation API to make this kind of transformation possible and to keep the code coverage feature, but still be able to move forward to Jack and Jill. And that's going to happen this year. So maybe at this level, we would be able to use bytecode weaving, and that would be interesting for the whole platform because we can do something that is even more faster than annotation processing. For instance, if you would bind a field a la butter knife, you would still need some reflection to actually find the binder which binds the field. But with Transformations API, you could just take your class, and as soon as the layout has been inflated, you replace all the fields by the values of XML, and that's it. So that could be an opportunity to make reflection faster if they don't want to improve the art JVM. Thank you very much for attending this reflection on reflection. If you have any questions or comments, they're welcome. Thank you.